this video, I'll talk through the 2025 National 5 Physics paper and explain how I would approach each question, starting off with the multiple choice. In the first question, we're asked about scalars and vectors. For the scalar values, we want something that is fully explained by just the size of it or the magnitude. That would be things like distance, mass, that looks like that. And then vectors, we need to know a direction to understand what effect they will have. Forces, velocities would be the ones for that. And that means that the correct answer is B. Question 2, we're talking about the displacement. An important thing to note here is that at the point where we cross over the time axis, this is a change in direction. We have to treat each of these sections separately. So we're going to deal with the forward section first and then the backward section. It could well be that the object was moving backwards and then forwards, but I'm just doing this to keep it right in my head. So we're going to have half of the length, which is 1.5, times the height, which is 6, which is going to give us 4.5. And then the backwards one is half times, so the length this time is 0.5, times the height, which is 2. That's going to give you 0.5. And then we take them away. Or if you put in the fact it's -2, maybe you're supposed to do that. But -2 would then make that minus 0.5. Same thing. We'll get to the same answer of 4. Take away 0.5. Gives you an answer of 4. So the key thing there is at this point here, we are changing the directions. We need to treat the part before that and after that separately. Moving on, we're asked about final speed 1. We're given acceleration. We're given a time. We're given the final speed, which is v, and we have the initial speed, which is u. Well, if a equals v minus u over t, rearranging this, well, that means that at would equal v minus u, and u would equal v minus at. Plug in your numbers, so 5 take away. I have to be careful here because we are slowing down. That means we're dealing with a deceleration. That means when I'm putting in my numbers, it's going to be 5. Take away what will be -2 times 8, which is going to be 5 plus 16, which equals 21, which gives us the answer of D. And this one we're dealing with our pairs of forces. We have opposite and equal. So downwards force on the table. So cup on the table means table on the cup. And that is just what A is in. So yeah, read the part that they're telling you, and then you want to flip round what is pushing on each other. Next one, we're talking about the work done in lifting the crate. Now, to lift the crate, we're going to be increasing the potential energy, H, which is going to give us, so the mass is 180 times by 9.8, and then times by 3, which when rounded gives us the answer of E. Another way maybe we could have done is if we want to use the EW equals F times D. Well, the force acting upon this mass would be its weight, and weight equals mg, so you'd be timesing the 180 by 9.8 as well, and then times it by 3 because the distance moving is 3 meters as well. So you get the same answer for that way. Not sure which one's preferred, but that's the way I would do it here. And this next one, we have a mass, we have a speed, and we are asked for energy. Now it's moving, traveling. This is sounding to me like kinetic energy, which would be EK is a half mv squared. So EK is a half times 25 times 9,200 squared. Plug that into the calculator. We have 1.058 times 10 to the power of 9. A little bit of rounding. Yes, there's D. There. Would work out for that. And importantly here, this is presuming that all of that energy, all of that kinetic energy is converted into heat energy. If there was any heat losses, then your value would be a bit lower than that. Next up, we were given a relationship, presumably one that you're not taught in the course. We are then going to plug in our values. So V equals the square root of our G So V equals, so R is the total distance from the center of the Earth to the satellite. So we have the radius from the center of the Earth out to the surface of the Earth. We also have to include the fact that the satellite is above the surface of the Earth. That's looking like the distance that we're dealing with is going to be the radius of the Earth and the height at which the satellite is orbiting together. And I'll just do that over here. So R is going to equal 6.4 times 10 to the 6. Add on that 3.6 times 10 to the 7. Make that to be 4.24 times 10 to the power of 7. So our answer is going to be the square root of 4.24 times 10 to the power of 7 times the gravitational field strength. Now they're given it for that particular height. So we need to use that value, not the 9.8 we use when it's just talking about on Earth. Let's do that then. And we get that to come out as 3,054 meters per second. Again, rounding, we get to C. That's the answer. So just watch out. You're gonna have to take both the distances together to get the total distance away. In this one, we're dealing with the moon. Nope. In this one, we're dealing with the weight of an astronaut on Earth compared to Mars. So we're going to want to use W equals mg. Do the Earth one first. If we can work out the mass by doing the weight divided by gravitational field strength, we can then sub that in to check what they are on Mars. So we've got 710 divided by 9.8. Out as 72 point around to 45 kilograms. And then on Mars, W equals mg. So the weight will equal 72.45 multiplied by Mars 3.7 newtons per kilogram, 268 newtons, rounded to 270, giving you C. Okay, and this one we're using light years, which is the distance travelled by light in 1 year. Okay, we need to do the speed times the time. So the speed of light is 3 times 10 to the power of 8. You can find that in your relationship sheet. Nope, you can find that in the data sheet. When it comes to time, we're talking about how many seconds are in, well, 1 year we'll start with for that. So that'll be 365 times the 24 hours times 60 minutes times 60 seconds. Importantly here, we have got 8.6 light years. So it's going to be 8.6 times all of that together. And for slight ease, I'm just going to fire those all into the calculator, taking my time to input it correctly. That goes 8.14 times 10 to the 16 matches nicely to E. So we need to make sure we're grabbing onto our speed to put that into the calculation. Next, we are doing a line spectrum. We are looking for matching up the lines in the star to the lines of the different elements. If hydrogen was present, there'd be a line here to match up. That is not the case. Helium, I'm looking for things like this double one is quite distinctive, which we do have. We've then got this part here as well. That works out nicely. So all the ones from helium are there. Carbon would bring this big, thick line there. And then it also would bring some of this part, some of those lines in there. That's looking good. Nitrogen would need a triple line. Don't have that. It's looking just like helium and carbon. And if I'd read the question, we're only wanting 2 of them in it. So helium and carbon looks good to me. Shuffling on, we're talking about AC and DC. Direct current travels in one direction. Both X and Y are traveling in one direction. Whereas in trace Z, it is changing direction, making that an AC, an alternating current trace. E is going to be your answer for that one. Dealt with. Here, we're talking about the paths taken by a particle as it travels through the field. Okay, when the particle gets close to Q, it is drawn towards it. That is suggesting that the particle would have an opposite charge to Q. So if you look at the options, A has positive and negative, so that could work. B doesn't look like it'd work because this would repel each other, which isn't what's happening. C could be right, D could be right, E couldn't be right. We then need to look at what happens with R. Now, it's also getting pulled towards R. If R was the same charge as the particle, it would have repelled the particle, and that's not what's happening. So I'm going to say that Q and R have to be the same, and then the particle is the opposite of those two. So let's look here. Well, A looks like it would work because that was positive. It would be attracted to the negative Q and then attracted towards R, which would work. Versus, yeah, the other ones have got them opposite way around for that. So it's attracted to Q and then attracted to R. Q and R are the same charge. Particles opposite charge. A for number 12 makes sense. In this one, we're trying to work out the resistance of resistor R. Now, they tell us that the voltage across this resistor is 3 volts. The other one has to have 9 volts because the voltage is being split in the series circuit. If we have 3 times as much voltage, the resistance would have to have been 3 times as big. And then 3 times 240 would give you 720 ohms as your answer. If we're using a relationship, the relationship that could help us. So this one here of V1 over V2 equals R1 over R2. I'm going to make R1 the one we're trying to work out. So 9 across that. So 9 over 3 equals R1 over 240. Change it up to get R1. So 9 over 3 times 240 would give us our R1. And that will come down to 3 times whatever it was, which is the same thing we ended up doing, just more instinctive rather than using the relationship, but both of them would work. So because we know, or we can work out all of the voltages involved, and we're given one of the resistances and told to tell them the other one, we get our way to the answer there. Next one, we want the total resistance between X and Y. Right, looks like we need to deal with these in kind of 2 separate parts. So we've got the initial resistor as the current's passing through that, so that's going to be 12 first of all. And then over here, we're going to have to work out the resistance of the parallel part. Just make a wee note to keep track of it. So that's going to be 1 over 12, add 1 over 12, so 1 over RT is going to be 2 over 12. Right, 2 over 12 is 0.166 recurring. And then we want to do 1 over that value to work out what RT by itself would be. So RT there be 6. We then have to get the total. To get the total for the whole circuit, we have to do 12 from the original one plus that 6 that's in the parallel section. That's going to give you 18. Matches D. That's your answer there. Next one, we're asked about power. We have the current. We have the resistance. Okay, right. And we have the total voltage. Right. This is might be one of those ones where we've got a few different ways we want to do it. Reading the ammeter is that. So we know. Oh, right. Resistance. I missed that bit. So we know the resistance of both the parts. For there. So that has a resistance of 8 ohms. Now we might be best doing the finding out the voltage across the component. Because this time we know the supply voltage. So the voltage across the lamp would be the 8 from it over 8 and 16. And that's going to be times by 12. And then that's going to be 8 over 24 times 12. That's going to give you 4 volts. And then as a wee aside, if that's 4 volts and this is 8 volts, that, going back to what I said earlier, makes sense because we've got double the resistance across the resistor. So then it's split unevenly in that way. We then want power, so P. A few options for the power one. I just worked out the voltage. So maybe IV would be a good one. That's going to be the 0.5 amps times that 4 volts that worked out. And P would equal 2 watts, which gives us A as our answer. Thinking back, could we have actually just used the other ones with what we're already told? Yeah, that would have been easier, wouldn't it have? So P equals I squared R 0.5 squared times 8. And that also gives you 2. Yeah, that saves us having to do any more calculations for that. But we got the same answer. It's all good. In here, when we're using main supplies equipment, there are thresholds that we could have memorized. That would be 720. So up to 720 watts. 3 amp is suitable. And then above, we want the 13 amp. Something to watch for is here we're dealing with kilowatts. That's going to be 2,600 watts. So that would need the higher rating, which gets rid of A and B. The television is below, so 3 amps would be fine for that. And then 900 is above that, so we want to go back up to the 13 amp. Only one that is suitable, the only one that has it correct for all of them would be B. I'd thought for a second there that you could have worked out, if you were given more information, you could actually have worked out what the power rating, what the current would be, and you want to have a fuse that's above the running current, but not way beyond it, because otherwise it's not going to act as a safety device as it's supposed to do. Moving on. In this one, we're looking at the specific heat capacity of water. Right, experiment procedure improved. Insulate the beaker to reduce heat loss to soundings. Well, that'll give you a more accurate value because all the heat's, or more of the heat's gone into the water. Move the immersion heater into the water further. I suppose that would then maybe be helpful because at this point here, some of that heat could escape. So that sounds quite good to me. Use a stopwatch to work out. Well, if you're working out the energy supplied to the heater using power equals energy over time, then yes, you would want to have as accurate a time as possible. But they are using a joule meter, which is going to work out the energy supplied straight away. So we're not relying on a calculation. So in this particular setup, that wouldn't make a difference. Meaning 1 and 2 are correct, giving you an answer of C. So in some situations when you're calculating the energy, you'd want to have the most accurate time you can. This one, it wouldn't actually make a difference. Moving on to 18, we're talking about the changes in temperature over time where we're cooling something. We could go gas to liquid to solid. Now, if you find yourself in a position where you've kind of forgot which parts are the changes of state and which parts are the different states. So, for example, here, this would be our condensation. And then we're going to be freezing over here. Now, if you can see here, we've got 1, 2, 3 slanty sections. And we've only got 2 flat parts. Well, the flat parts are the changes of state. And then each of the diagonal parts are when they are either solid, liquid, or gas. Now, from what we are talking about is we've got our gas, liquid, and then solid. And then here we've got condensation. And here we've got freezing. Right, what's the question asking is, the boiling point is 120 degrees. That would be when it goes from a liquid to gas. And that is going to happen at this temperature here, which is 120. That's looking good to me. At time of 40, the substance is a gas. Well, no, because it's the liquid starting to turn into a gas. So that's not looking good to me. And then the melting point is the point at which it turns from a solid to a liquid, or liquid to solid. That's going to be here. That is at 20. That to me is... Where have we gone? C. Moving on, we're talking about pressure. Pressure, weight, area. That's looking like a P equals F over A. Now, the P, so we're working out pressure. The weight, the force downwards is 520. Now, importantly, it says the area of the platform on each shoe is this value. Well, the ballet dancer is contacting the floor with both shoes, which means I'm going to have to use 2 times the 1.6 times 10 to the minus 3. Plugging that all in gives 1.63 times 10 to the power of 5 pascals. And we have got that, hopefully. That's looking like D for that one. If you had not taken into account both the shoes, the pressure would be doubled what it actually is, because that's you calculating it going through only one. But next up, another pressure one, but this time we are dealing with temperatures as well. So the volume remains constant, so we don't care about the volume in this one, but we are talking about temperature and pressure. So P1 over T1, P2 over T2. First of all, we want to turn these into Kelvin by adding on 273, so 293 Kelvin and 308 Kelvin. Okay, I'm going to make the pressure we're trying to work out P1. So P1 divided by what its temperature is 308. And then the other combined things. So the original pressure was 1.9 times 10 to the 5 all over 293. So P1 is going to equal 1.9 times 10 to the 5 over 293 times by 308. If the temperature's rising, the pressure should go up. Think of it heating up a tire, heating up a balloon, and it starts to expand. So I'm hoping that this number is going to be above the original. And that gives 1 point, well, it's going to round up to 2 times 10 to the power of 5 pascals, which matches answer D. For that one, actually now thinking about it, if we just think about the pressure would go up because it's expanding, then they would all be cancelled out because they're all lower than what we've got. Calculation shows what the correct answer was, but I suppose if you're looking, we're only going up by 15 degrees. It's not going to go up as much as that, maybe. Calculation works. Let's do the calculation and get the answer that way. If you were given other information about them, you would use one of the other relationships to be able to work them out. But I just always look and see, right, well, it says that remains constant. Ignore it. We don't want to include volume. Look for the one that then has the other two, pressure and temperature. In this case, we're wanting wavelength and amplitude. Wavelength is the length of one wave, funnily enough. Chop, chop, chop. There are 3 waves. So 3 waves in 120 millimeters. So one wave would be a third of that, which is going to give you 40. And then the amplitude is half the height. So from the center up to the top, well, the height is 0.2. So the amplitude is 0.1. 40 and 0.1 gives us B for an answer there. Nice and straightforward. Next one, the band of electromagnetic spectrum these clues refer to is... Okay, so we need to have our electromagnetic spectrum memorized. There are songs that can help with that. I shall not sing them to you. Right, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. This is the longest wavelength. So therefore that's the shortest wavelength. You've then got the highest, lowest frequency. So wavelength and frequency are the opposite way around. So longest frequency, highest frequency. Right. So a greater frequency than greater frequency than microwaves. So that means that it's one of the ones past here. And then diffracts around objects more than visible light. So that means it's going to have a longer wavelength because they're more affected by passing around an object. And then this one, greater frequency, means shorter wavelength. So that can only then be infrared radiation, which is going to give us B. So because my background's chemistry, I'm more inclined to think about the length of the waves rather than the frequency, because that comes up more often in chemistry. And that's, my approach to that. Another thing that could kind of help is, so let's say we got, hopefully the frequency one's the one you've got nailed down, sorted, fine. Well, we're now in a position where you've got visible as the clue for clue 1. Now, if it was asking you for a shorter wavelength than visible, well, you've got 3 options. It could be ultraviolet, X-ray, and gamma all have shorter wavelengths than visible, but they only want one answer. So by kind of thinking it through then, well, even if you can't remember about is it bigger or longer or shorter wavelengths that diffract more, well, it kind of lends itself to being the one that you can narrow in on and get it to infrared. But though you might have better ways of doing that than me, but that's what I kind of was thinking as I picked out my answer. Next up, we're dealing with nuclear decay and nuclear disintegrations. I think we're just trying to be fancy and talk about them decaying. We have activity, we have time. So A equals N over T, the number of decays over the time. And if activity equals the number over time, and the number equals activity times the time. Careful, we have got an activity in mega. So we'll go kilo, then mega. So that's going to be times 10 to the power of 6. And then this is going to equal, we need it in seconds. So times it by 60 to turn it into minutes, 72. And then times it by 60 again to turn it into seconds, 4,320, 4320. And then 2.2 times 10 to the power of 10 gives us an answer of E. I would presume that some of the other ones are if you forget to scale up into mega or do that incorrectly. Maybe if you forgot to do the time thing as well, you'd end up with some of the answers. This one we're talking about equivalent dose rate. So we have activity, absorbed dose, equivalent dose rate. Now, what are we told? Our activity dose rate is the equivalent dose over time. And then this time we've got micro. So 480, well, going down the way, you go from normal sieverts to millisieverts to micro. So that's going to be times 10 to the power of -6 all over. Well, you turn this again into seconds, so 300 seconds. I've just noticed something right. I'm going to do this anyway. So I've just clocked there that if you look at the answers, they're all in micro anyway. So we should have or could have just left it as micro. Sieverts putting it into it. 480 times. So I get that out to be 1.6 times 10 to the minus 6 sieverts, which is 1.6 micro sieverts. I was so on autopilot about always making sure, I'm sure your teachers have said that as well, making sure you got things in the right units. But because we're dealing with micro sieverts at the end, it could have been slightly simplified by doing that, but still get the answer of A. And again, I would have hopefully clocked. I did clock that because my units aren't quite the same. I've missed out the per second in both of them. But you get the idea. Next one, we're talking about particles combining, they're joining together. That is going to be fusing together, giving you B. Fission would be then splitting apart. Alpha would be giving off a helium nuclei, giving off electrons, emitting electromagnetic radiation. So B is correct there. Moving on, we are asked to work out the magnitude of the resultant displacement of the gardener from point X to point Y. Okay, so I'm looking to make a triangle. That most important one is the line from X to Y is needed. Now, I could go along to here and straight down, and that makes a lovely little right angle triangle. Let's start putting in our numbers. Well, up and down the way, it's 32 to here. Another 4 gives you 36 meters, and then across the way is just matching up that 15 meters there. So this is us using Pythagoras. People write it in different ways, but the squares of these two added together will equal the square of the one we're trying to work out. So the square of the displacement is going to equal 15 squared and 36 squared. So our value is going to be the square root of 1521, which gives us 39 meters. And then our next job is to work out the bearing of the displacement. Now, we could use the value that we just worked out, but I'd prefer to stick with the ones from the question. So if we made a mistake in the previous one, it'll still run smoothly. You can still get follow-on marks, but I just think it's easier to start with the ones they've given us. Now, the angle we care about is this angle in here, and we then can start labeling our different parts to be able to use SOHCAHTOA. That is your hypotenuse. This one's opposite the angle I care about, and the other one's adjacent. And the tan of our angle is going to be the opposite over adjacent, TOA, which means that our angle is going to be inverse tan of 15 over 36, which means our angle is going to be 22.6. I'm going to round it to 23 because that will make life easier when it comes to the next bit, which is your angle has to be from north. So when we look at what's going on here, well, if it was going straight up, that's a bearing of 0, 0, 0. And we are 23 degrees before that. So I would say the easiest thing to do to get your bearing is going to be, well, if it was all the way around, it'd be 360. Take away 23, which gives you 337 as your bearing. We don't put degrees because it's a bearing measured from north for that one. And that, for me, would be the easiest way. Slightly awkward ways you could go all the way around there would be 270. This section in here has to add up to 90. Well, if that's 23 here, then up to 90 would be 67. And then 270 add 67 is 337. But that just seems like a long way for a shortcut for that one. Next, we're asked to work out the velocity, which is the displacement over time. And because it's a vector, we have to remember and bring that 337 bearing with us when we give them the final answer. So S equals V bar T is what we're going to use. So V bar equals displacement over time, which would be, 39 meters from before over the 55, 0.7, let's go 09, and that would be meters per second at 337, just like that. Next one, we're asked about average force work done. That is EW is FD. So work done equals the force times the distance. So EW is, well, the force is 6 to 8. And then we worked out that the distance we were talking about was 39. What's it? Oh, no, wait, distance. Distance, not displacement. Sneaky people. So we actually need to count up all the parts. So in distance, it's just each of the legs of the journey added together. So it would be 32, add 15, add 4, which would give you 40. 47, 48, 49, 50, 51 meters. Distance covered. Sneaky, sneaky. EW would give 3,468. I'll round it to 3 significant figures. Let's go 70 newtons. Nope, not newtons, joules. Energy. For joules, and that would pick up your mark there. Next one, we're talking about the weight at launch. W equals mg. W equals, what's the total mass? That's everything involved. So I'm not seeing anything sneaky here. 10 to the power of 6 times, what's 9.8 because we're on Earth. So W equals 1.4 times 10 to the 7 newtons. And then we are told we have upwards thrust. Calculate initial acceleration. Okay, so the thrust first has to counteract the weight, and then it's over and above the weight that would cause the acceleration upwards. So if I sketch a wonderful rocket, wonderful. So we have our weight acting downwards. We have the thrust acting up the way. So we want to calculate the unbalanced force. And that will be to this one. Take away the weight. And then acceleration. Well, if F equals ma, then A equals F over m, which is that number we calculated, divided by the 1.43 times 10 to the power of 6. Yes, it was. Then A equals 6.15 times 10 to... No, not times anything. Which is 6.15 meters per second squared. Like so. Okay, next one, they're talking about the payload fairing sections which protect the satellite. They're detached and re-enter the Earth. Show all the forces acting on one of the payload fairing sections as it falls vertically through the Earth's atmosphere. Okay, job 1. You're going to have the weight, and you're going to have the air resistance or air friction up the way. Air resistance. Just like that. There's nothing powering, nothing forcing, it's just dropping, falling as it goes. At one point as it falls through, a parachute attached to it is open. This causes an increase. Nope, this causes the speed of the section to decrease rapidly. In terms of forces, how does that do it? Well, that's going to then increase the air resistance. And then that's going to produce an unbalanced force upwards. And that's going to be what reduces the speed. Right, at point P in this one, we have a constant speed. And if the speed stays the same, that means that the forces are balanced. Right, now let's put some numbers in. Well, if the weight downwards is 9300, if there was no upward force, that would be the force that's causing the acceleration. But they're saying here there's no acceleration, no deceleration, it's staying the same. So the upwards force must equal the same number. So upwards force 9300. Okay, I said speed, I just read it. It says velocity instead. Same, doesn't change, only change that one word. You have constant velocity means the forces are balanced. They have the same magnitude. And there, in this one, we're talking about ski jumping and why the ski jumpers adopt the different positions. At the time of this recording, the Winter Olympics has just finished, and we're in the middle of the Winter Paralympics in Italy. And if you've watched any of the events, you might have heard or thought about the different forces involved as they're going through them. In these questions, you get 1 mark for showing a limited understanding of the physics involved, 2 for reasonable, and 3 for good. Doesn't have to be very good or excellent to pick up all the marks, and hopefully my answer will be able to pick up all 3. So one thing that will affect the length of the jump will be their takeoff speed. A higher takeoff speed will result in the jumper travelling a further distance. The gravitational potential energy that is gained by moving up to the top of the ramp is converted into kinetic energy, and the heavier jumper will gain more kinetic energy because they will have a higher gravitational potential because it's involving mass with the mgh, and that will allow them to reach a higher speed and then travel further. In terms of the equipment, having low friction between the skis and the snow would also help increase the takeoff speed, reduces their losses due to the heat from the friction. When in the air, the weight is going to be dragging them down. That is mass times the gravitational field strength. That will be higher, the weight will be higher for heavier jumpers, so they'll have less airtime, but they'll be hurtling through the air more quickly because of their mass is greater as well for that. So they would be losing their horizontal speed more slowly, so they can again go further, even if their time of flight is less. Their streamlined aerodynamic position, as you can see from here, and also their tight bodysuits will reduce air resistance, which should keep them in the air longer and travel a further distance. The shape as well, they want to have takeoff height that is not too low that they just fall straight to the ground, but not too high that they lose momentum overcoming the ramp. So they're all worked out in specific ways to help maximise the distance, because as spectators, people want to see the longest and biggest jumps that they can. That's everything I can think about putting in for this question. That should hopefully be more than enough to pick up the 3 marks for a good answer. Moving on to question 4. And this one, they're asking, why would the spacecraft want to pass close to the planet Mars? Well, that's to do with the slingshot effect, and that's going to increase their kinetic energy. So they'll be traveling faster towards the, where's it going? To the asteroid. That's what we're going for. Journey, ion drive, engine thrust, small unbalanced force. Why can a small unbalanced force result in a large increase in speed? I'm thinking this must be something to do with the lack of air friction in space, which would mean a small unbalanced force, it acts over a long period of time. We are asked about solar cells producing less power as it approaches sight. So we're heading away from the sun then. Is that just what it is? That as solar cells are moved further from sun, which is the energy source, the light source, less light energy is received, trapped, absorbed. It's the time of one orbit. There are, so 41 orbits is 56 days. So 1 orbits we are dividing by 41. So 56 over 41. 1.37 days for every orbit. After 56 days, we move to an orbit closer to that. What will have in the orbital period? That will have to decrease because it's a shorter distance. So if it's a shorter distance, it will take less time to travel around that distance. So that should be decreased. And this question, we're asked about how the Van der Graaf generator is working. We have got a positive charge building up on the dome, and then we have the dishes flying off. Now, for them to repel each other, they would have to have the same charge. So the dishes are also positively charged, and like charges repel. And this one, we want the average current. We have the charge, which is Q. We have time, although we need to remember to turn that into seconds, and we're asked the current. relationship sheet, Q equals IT, milliseconds is 10 to the minus 3. So our I is going to be the charge over the time. 2.5 times 10 to the minus 6 divided by 0.8, and milliseconds is times 10 to the minus 3. That gives us 3.13 times 10 to the minus 3 amps. We're then asked about the number of electrons transferred during this discharge process. Okay, so it tells us that 1 electron is 1.6 times 10 to the minus 19. And we have to work out how many electrons give the 2.5 times 10 to the minus 6 coulombs. Okay, so any of these kind of scaling up, scaling down, I like to go through what 1 would give us. Now, to go from any number down to 1, we can divide by that number, 1.6 times 10 to the minus 19. And then to go from 1 to any number, you times by that number. So times by 10, 2.5 times 10 to the minus 6. So we need to do the same to 1 because it was 1 electron. So our number of electrons is going to be 1. And then do the same things on the other side. Divide by 1.6 times 10 to the minus 19. And then times by 2.5 times 10 to the minus 6. 1.56 times 10 to the 13 electrons. And the reason I like doing things this way is, let's say for talking sake that this information was for 100 electrons. Well, that would just mean that you'd do the dividing and times into whatever you start with, the 100. So for me, that works really nicely for any kind of scaling up, scaling down things. Like so. Next one, we're asked to complete the circuit diagram. Okay, to show, right, we're trying to measure the current in and the voltage across the resistor for a range of voltages across resistor R. Right, so and probably first one, so let's connect up here. Now we then want a voltmeter across resistor R. So we want to put it coming out like that. Let's just join those two up. And then our voltmeter would be drawn like so. Connect that in, and then we're going to want our ammeter, which is measuring the flow of electricity. So if I put an A there, so the ammeter would pick up the current that's traveling through position R, and then we're measuring the voltage across the resistor as well. And then by using the variable resistor, that needs to be included because then you can change that, which will affect the voltage across the resistor R, I would presume. But yeah, voltmeters across and then ammeters within the circuit would work out nicely. Determine the gradient. No, using the gradient, determine resistance R. Okay, so we want to pick 2 points on the graph. So ideally it would be ones that are sitting nicely on numbers, or are we just starting from the bottom one? So we could take this point here, which would be, so it's 2 little boxes up, so that would be 0.2. So our first point, make it x1, y1, would be 0 across and 0.2 up, and then x2, y2 would be, let's go maybe here, comes out pretty well, bang on 0.05. So it's 0.05 across, and then it's 3.0 on the y-axis. So the gradient, y2 minus y1, x2 minus x1, 3 take away 0.2 over 0.05 take away 0, 2.8 over 0.05 gives you a gradient of 56. If our gradient is 56, now if you think about the relationship between voltage, current, and resistance, well, V equals IR, and R equals V over the current. Well, that's what we were doing. The Y is the voltage, and then the X is the current. So that's why the gradient is spitting out as the resistance. So that gives us a resistance is equal to 56, and then that's ohms. Like so. Next on, what's the conclusion about the resistance? Well, the current is increasing. Now, in this one, we have a curved line. We don't have a straight line. Up here, we had a straight line where the resistance is fixed. So if we took other points, you'd get the same number for the gradient, which means the resistance would be the same. This means that there's a changing resistance. So in this way, in a parallel circuit, if one of the, in this case, LEDs breaks, the rest of them would stay on. If one LED, or spotlight, let's go for that. So if one spotlight fails, the rest stay on. Next one, we're talking about each of their power supply total current. Okay, well, if each one has a power rating of 4.8, power is going to equal 4.8 times 4, 19.2 watts. And to work out the current, we also need voltage, which we've got up there is 12. So PIV is looking like the best one. If P equals IB, I equals P over V, 19.2 all over 12, 1.6 amps. In this one here, we've got component X. Component X is a MOSFET. That's one of the ones you just need to remember. You need to memorize them. MOSFET. Explain how it activates as it gets dark. Okay, so we have got an LDR, and this is going to be your LURD, light up, resistance down. So as the light decreasing, I'm just going to add in level. So light level decreases. Or if it's light up, resistance down, then light down, the resistance of LDR increases. And then that's going to mean that the voltage across the LDR also increases. Now, in the variable resistor part, the voltage across the variable resistor would go down, but we only care about the bit at the bottom because that's the bit that feeds into the MOSFET. So once we've got that, once it gets to a certain threshold, a level, a value, once the voltage across the LDR reaches a certain level, that's when your MOSFET is going to turn on. And if it's a temperature 1, that would be the third temperature up, resistance down. And like I say, if this was the other way around, we would be talking about, well, the resistance of the component is going to go up or down, which changes the voltage across it. And then in some questions, if that was at the bottom, you'd want to talk about the voltage across the variable resistor, but there's no need to do that just now. Here we have our second using your knowledge of physics question, and we're asked about a circuit and how it works. Okay, what things we talk about? Well, electrons are not fired out of the battery. The electrons are already in the wires. It's the battery providing the potential difference, the voltage that provides the energy for the electrons to move around the wires. So that's the first point that's incorrect. Electrons don't get converted into light, but the electrical energy is transferred to the lamp. And then depending on the efficiency of the lamp, you'll get light and some heat. And it doesn't tell us what type of lamp we're dealing with. So I'm going to talk about like the filament one, the wee spirals that get warmed up by it. So the electrons are still present in the circuit, but that energy is passed over and converted by the lamp. Next, they talk about adding another lamp and making the lamps dimmer. It depends on if it's going to be series or parallel. So if it was in series, that would increase the total resistance. Resistance opposes the current, so the current would decrease, which would decrease the power, which would make it dimmer, like they said. If the lamp was added in parallel, you'd have the same brightness of each lamp, because each of the branches of the parallel circuit would have the same voltage, so they would still be the same brightness of it. Again, with these ones, there's probably more things that we could talk about. That would hopefully be enough to pick up the 3 marks for being good. Next one, we're now talking about energy and the properties of matter. We are told our mass of the water. We've got our initial temperature. We're asked about energy. And we're told our final temperature. This is very much feeling like an EH equals Cm delta T. EH equals it's the specific heat capacity of water, which is 4,180 joules per kilogram per degree Celsius. And this is one where I always have to pause, because in chemistry, sorry to bring it back to chemistry, but in chemistry, it is 4.18 because it's in kilograms. Kilojoules per kilogram per degree Celsius, whereas here we're talking about joules. So 4180. The mass is 0.38, and the temperature change is 22 degrees. And that gives us 34,900. I need to do a bit of rounding. Let's just go for 9. So 34,900 joules, which would have been 34.9 kilojoules. For that one, next up, power. So the time taken for it to reduce that by there. So that's just sounding like what we've just talked about. And there, in time now, P equals E over T. The energy over the time. So therefore, time is going to be the energy over power, which is going to be 34900 over 120. So our time is going to be 291 seconds. That one, it'll depend on how far you rounded this value here. You'd end up with slightly different values, but they'll take that into account as you're getting marked. Next one, the time taken, heat gain from surroundings. One way they could improve this. This feels like the question earlier on about how you would insulate it. So just insulate the machine. Or like put a lid on it. That's kind of insulate as well. But just make like a thicker container, like if you have like inside an ice box and they've got the kind of polystyrene insulation there. That should do that. Overcome that problem. This one, once it's at that, there's more energy to make ice cubes, so there's no temperature change here, which would mean instead of EH equals Cm delta T, it would be EH equals ML, so the latent heat one, which I have totally lost. There we go. So ML. So let's do that then. So EH equals ML. So EH equals, and it was, wait, are we trying to get the mass? Oh, we're trying to get mass, never mind. Right, so we want M. M equals EH over L. So M equals, and we want it in joules, not kilojoules. It's not chemistry. So 15.3 times 10 to the 3 all over Now we are going from a liquid to a solid. And the reason that's important is there are two values that we could be given. So we have heat of fusion or heat of vaporization, vaporization gases, vapor. We're not dealing with that. We're dealing with top one, and water is 3.34 times 10 to the power of 5. And then this will give us a mass in kilograms, which is 0.0458 kilograms. That's our final answer. Moving on, we're varying the volume and measuring pressure. Kinetic model, pressure of air in the syringe. Well, it's all about the forces and the collisions with the walls. Air particles collide with walls of syringe. And that's where if you increase the temperature, the collisions are more forceful and there's more of them. You decrease the volume, they're going to collide more often because they're packed into a tighter space and things like that as well. They have went for calculating the value of 1 over volume and then relating that to the pressure graph. Lovely jubbly. Right, what have we got then? Right, along the bottom then, we've got 1 over volume, which is in milli, or reciprocal milliliters, so ml to minus 1, just copying the table. And then up and down the way, I'm going to put my pressure, which it says is in kilo pascals. Set up like that. Right, looking at the volumes range from 0.05 up to 0.25. Now, it looks like we could go for every big box is 0.05. And then that covers everything we need and is going up evenly. So that's looking decent to me. Pressure goes up to 160. 20s is my first thought. We've got how many boxes? 1, 2, 3, 4, 5, 6, 7, 8 boxes, 9 boxes. So going up in 20s would probably be quite a good idea. Another nice thing about going up in 20s is every baby box is going to be 2. And that's going to make that 10. So it should make our plotting a little bit more straightforward than other numbers. But as long as it's even scale and takes up half the page, you will be fine. Even if your plotting might become a little bit more tricky. 160. I've got the top 180. And then all we need to do then is just plot each of the values. So 0.05 is 32. That looks good. Then it's 0.01. So in this line, we want 67. So 60 would be here. 62, 64. Nope. 62, 64, 66. So 67 will be just in between. That should be there. Because then that would be 68 and then 70. So I'm quite happy with that one. Okay, next we're at 0.13. Well, and across the way, every 2 boxes will be 0.01. So this would be 0.011, 12, 13, 14, 15. And it was 13, so one little box past it. And it goes up to 81. So 2, 5, 3. And then 81 would just be half a box up. No, yeah, half a box up. That should be like there. Then we get to 17, which would be 4 boxes along from there. 17 goes to 112. 1, 2, 3, 4. 110. 12. Maybe just do this afterwards. 7, yeah. And then 2, 5 for the last one. Straight on a line, which is nice. Up to 160 on a line as well. So they're actually quite decent on that one. So they've been a wee bit awkward, but they're not all sitting neatly and tidily on each of those points. So it makes it a wee bit more tricky. But remember, every two little boxes is 0.01 going across the way. Just take your time and go through them. So 0.05, 0.10, 0. What was that again? 13. Yep, which is wanted. 15, 16, 17. So 0.17, yes. And then that's bang on the 0.25. So they're good. Up and down the way, checking them. Well, this is just above 30. Every box is 2, so 32. Then we've got 62, 64, 66, 67, which is what we wanted. 81 is just above. And then 112. And then 160. So that should be fine for that. We are then looking, is this more of a line or a curve of best fit? It looks very straight liney to me. Grab your ruler on a straight line. And actually, just joining those two there looks pretty decent. It's getting quite close to all of them. If when you put your ruler against it, it looks more curvy, you would need to freehand a curve of best fit. So something like that. You'd want something like that, but actually looks decent. The next one, we have to make a conclusion about the relationship between the volume of a fixed mass at constant temperature and pressure. So we're dealing with volume versus pressure. Watch out for the fact we did 1 over volume, so the inverse of volume. So as the inverse of the volume increased, the pressure increased. Pressure is inversely proportional to the volume. Yes, that works. Okay, using your graph determine at 148 kilopascals. Well, 148 would be 142, 144, 146, 148. So I'm just going to use a different color. So 148 would be 4 boxes up. We're going to run it all along till it meets our section. Run it down. Well, that has not gone very straight at all. I'm at the mercy of the thickness of my line. I'm going to just take that to the nearest box, which would be that box there, which would be 0.23. But again, that is 1 over volume equals 0.23. So volume is going to equal 1 over that. Gives an answer of 4.35 milliliters. Give away to improve reliability. You could repeat for reliability. So repeat at each volume, and then you take an average. And that means if there were any that were a wee bit off, this would reduce the effect of those. Next up, we're talking about transverse waves. So there's longitudinal and transverse. Transverse is is to do with different. This is to do with the movement of the wave and its vibrations. So they move and vibrate at 90 degrees to each other. So these are waves that vibrate at 90 degrees to direction of travel. Show that the frequency is that. We have got a few things. We have number of waves, we have time, and we have length. So for frequency, number and time is probably our best one. F equals n over t. So F equals 500 over, it's 30 minutes, so times that by 60. And that gives us 0.28 hertz, which is nice because you have to match it up. So if you get it wrong, you can tell because it doesn't match what it's saying. Calculate the average speed. So D equals V bar T. So then V bar speed equals distance over time. It is, the time is 32. Length of the pull 160. meters, which is 5 meters every second. Next, we want the average wave length. Now we now know the frequency and we know the frequency and the speed. So that looks like VF lambda. So if V equals F lambda, then lambda, rearrange it, equals V over F, which will be the 5 over, what's the number we worked out? 0.28. And this will give us in meters, which I presume is what they want. So 5 over 0.28 gives you 17.9. And that is meters. Done with that one. Next one. Satellite, altitude, time from the satellite to the GPS. So it's not going back. Sometimes questions will talk about like going forwards and backwards. It's just the one direction. So that shouldn't be too tricky. DVT again. So if D equals VT, then T equals D over V. So T equals 2O over speed. Microwaves are a part of the electromagnetic spectrum, which is light. So it's going to be the 3 times 10 to the power of 8. Now, I've looked at my number and it's looking really, really big, which is, I've now spotted, I forgot to check this one. That's times 10 to the 3 because it's kilo. It's kilometers, not meters. So that should then fix my answer. So that gives 0.067 seconds. This question can flag up the problem with some of the newer calculators who don't really like the powers or multiplying or dividing powers when you just write them all in a straight line. So if you'd put in just the numbers, as you would do in most calculators, and divide that by 3 times 10 to the power 8. Mine was not having a good time with that. Putting brackets around each of them helped. Or if you put it then in as a fraction, that can help as well. But it's just a bit of an annoyance with some of the newer calculators. Okay, state whether the GPS satellites are geostationary satellites. Their period is their time to do one cycle. If it was geostationary, it would be the same as the Earth, which is 24 hours. So it is not geostationary, as period is not 24 hours. If you can remember the orbit altitude, 36,000. I would need to have the same altitude that it's orbiting, which is not that. I know it's not that number. I think it's like 36, 35, 36,000. But yeah, time for it to do one period would be helpful. Infrared radiation detector and a rangefinder. What could we use for that? Well, you have photodiodes. Another option would be a light-dependent resistor that would pick up on how much infrared radiation was coming towards it. Calculate the frequency. We have the wavelength. We go back to V equals F lambda. So this time we want frequency, which is the speed over the wavelength. It's going to be, again, because we're talking about part of the electromagnetic spectrum, it will be 3 times 10 to the power of 8. And then it's nanometers, so it's 9.904. And then nano is 3 steps smaller. So micro, milli, micro, nano, times 10 minus 9. Again, I'm going to use the fraction button for my calculator just to stop it trying to freak me out with wrong numbers. Minus 9 gives, let's go for 3.32 times 10 to the power 14. And then that's going to be in hertz as my final answer. And then next one, time taken between being emitted and received by the range finder. Okay, so this is the one where it's reflecting for that. So we have our range, we have our target, and the signal will go forwards and then come back for it as well. Okay, and we only want one way for that. Right, what would be the easiest thing to do for this? Now, did we work out? Do we have DVT? Oh, yeah, it's infrared, so it's going to be the same speed that we just used. Okay, let's give this a bash. So, right, D equals VT. So D equals 3 times 10 to the power of 8. And that times by 1.2 times 10 to minus 6, which gives 360. The distance to target is going to be half of that. I knew that thought would come in handy. So distance 180. We could have half that and got to the answer as well, because if it takes that long to go there and back, the time to just go one way is going to be half of that. So 0.6 times 10 to the minus 6 times by the speed would have given that answer as well. But I think that's probably the easier way, more flexible this way round. And this next one, we're asked about the different angles involved. We have the incident ray, which is the one coming in. And your incident ray, the angle between the incident ray and the normal is the angle of incidence. And then the ray, as it's passed through and changed direction, that is your refracted ray, which is the angle of refraction. Right, why is it changing direction? Well, when it travels into a denser object, it's going to slow down. So it is... So the light is entering a more dense material at an angle, and therefore it's going to, it slows down and moves towards the normal. Let's go for diffracts. Yes, the angle after it's refracted is smaller, so it's moving towards normal. Let's go for diffracts. Refracts even. Refracts towards the normal. For that. And then when it's coming out again, it would go back the way, go further away from the normal back to the original one. Ah, great. Right, so we are trying to get it. Is this the same picture? Yeah, right. So we want to have it going back to this original angle. Okay, so as the light went in at this angle from the normal, it has then, when it's passed through, it's now moved closer to the normal. When we come back out, well, we've now got the light at this angle to the normal. And then when it comes out, we want to have a bigger angle coming out. Now, I want to try and get it as close as possible to what we had originally. On this software, I don't have the protractor. But if you had a protractor, you can make it match up as best as possible. I would want to put on as well just a little arrow just to show that I am going that direction. Traveling down, and then we want to make it obviously a bigger angle than we had, preferably the same angle as we had up there, but something like that should pick up the mark. Question 14. In this one, they're asking, why have we to use gamma radiation for detecting leaks? Well, gamma radiation is the most penetrating. It will pass through different materials better than the other ones, so it's the only one that can go through. Gamma is the most penetrating, and that's going to let it reach the detector. Which then, next one is what's the half-life? There's two ways we can talk about. I prefer the one about activity. It's the time taken for the activity to half. Or you can talk about it's the time taken for half of the nuclei to decay. Followed up by which of these should be used for this investigation? Well, it had to be gamma. So that is going to rule out the bismuth one. In terms of the half-life, so that's too long because it would just keep giving out radiation. That's quite a short period of time for you to find out whereabouts the leak was, because you're passing the tracer through the water. So you've got a very small time, monitored over a few hours. So that looks like the top one. Yeah, a few hours. Maybe a wee bit on the high end, but so the 24 is what do I say about it? Well, first thing is gamma emitter has a reasonably long half-life. It's difficult. So 10.5 is unreasonable for that. Both of these two, 15 and 11, 10 hours, that gives you, what did the word say, a period of a few hours. Reasonably long. Yeah, suitable, reasonable. Something like that. Next one, determine the half-life. Well, we said it's the time it takes for the activity to half. Be careful, we are not starting up at 1400. The graph is not up there. So we are not looking at 700. That's a common mistake. We are looking here. So what are these going up in? Well, they must be going up in 200s. Nope, they must be going up in 20s. So that would be 1240. Because then that would be 1260, 80, and then 1300. So 1240. Now, if the start equals 1240, half would equal 620. That's one box up from 600. Grab that, run it across, run it down. That looks like halfway between 100 and 200. That would be 150 seconds. Predict activity at 700 seconds. Okay. Well, if we go back to this point here, 150 seconds, it equaled 100 kilobecquerels. Well, 700 is one half-life more. It's 150 seconds. So it would have halved again. So that would likely be 50 kilograms. Not kilograms, kilobecquerels. Kilobecquerels for that. Would you have been able to do it? If we kind of follow the curve. I suppose that kind of works. Maybe is that what the one does? Just kind of follow it through. If we had a nicer curve, then it would kick out at 50 there. Yeah, one of those ways. Perhaps. Next, we're asked about absorbed dose. That is the HDWR. H is, well, the equivalent dose is 0.25 times 10. Now, micro is times 10 to the minus 6. Times by X-rays. Let's find that down here. X-rays are 1, so it's not going to change anything. And then that will give us, what will just be the same, but it might look nicer if we do 2.5 times 10 to the minus 7. And it's grays instead of sieverts or microsieverts. Calculate the energy. Absorbed dose. So we can use the absorbed dose, energy, and mass calculation. So absorbed dose equals the energy over the mass. So the energy will equal the dose times the mass. The energy will equal 0.25 times 10 to the minus 6 times by how big's the passenger? 64 kilograms, which gives 1.6 times 10 to minus 5. And then this one is the one, so becquerel sieverts. No energy. Read the question. Energy, joules. For that one. Now, is there a chance that they did this deliberately to make us want to use this value in the wrong place? Perhaps. But absorbed dose is D a natural one we're going to use there. Ionization is when a particle or an atom loses or gains electrons. In physics, it's nearly always going to be losing electrons rather than gaining them. One precaution, keep a reasonable distance away, or you could use shielding. So either a personal protective equipment or by staying away from it, going round the corner and having stuff put in as well. And another one would be time, or limit time near the machine. Add in here. Yeah, distance 1 would probably be my top pick there. That brings us to the end of the question and the end of the paper. Thanks for watching. Goodbye.